Hello everyone. In the third part of this module on next generation fibers, I will be talking about polymeric rigid rod fibers. The approaches for designing high performance fibers using rigid rod polymeric structures. This approach is actually totally contradictory or opposite to the last approach which we had studied in the previous lecture. Here, instead of using a flexible material, we are using intrinsically rigid interactive polymeric chain structure. Intrinsically rigid interactive polymeric chain structure. If you remember or you can recall, in the end of the last lecture, I had told you that polyethylene has one limitation, that is it is low melting. The melting point of polyethylene is low. So, therefore, for certain applications where we need to use high performance fibers at higher temperature, it is not a suitable alternative. So, this particular high performance fiber may be more suitable for all such applications where polyethylene is not able to perform. So, the aromatic amides, heterocyclic structures and aromatic polyesters are the polymers which are intrinsically rigid polymers we are going to talk about. These polymers are also known as liquid crystal polymers. When I say aramids, aramids are nothing but polymers which have amide linkage, and amide linkage is directly connected to the aromatic ring. Kevlar is a para-aramid. Similarly, Nomex has got a similar structure, molecular formula is exactly same. The only difference is Nomex, the aromatic structure is connected to amide linkage at a meta position, whereas in Kevlar it is at a para position. There are other rigid rod polymers as well, which are known as polybenzezoles. In short, I can call them PBX. X could be oxygen or X could be sulfur. So, based on that, they are known as PBO, polybenzoxazole or polybenzthiazole. If you notice in these structures, in addition to the benzene ring, it has got a fused 5-member ring, and this fused 5-member ring gives it more rigidity compared to aramids. And if I look at another structure which is M5 polymer or PIPD, it is even more rigid or less rigid? Any guesses? It is even more rigid compared to PBX. The reason is the central ring is not a benzene ring, it is a pyridine ring. It has got a hetero atom, it has got nitrogen in the aromatic ring, and in addition it has fused ring along with it. So, among all, this is the most rigid structure, right. So, all these rigid polymeric structures would give us liquid crystal properties. Now, what is liquid crystal property? You may say that you have heard of either liquid or crystal. Liquid means something which will flow, and crystal means something which is solid and it has a definite shape and size. The molecules are organized in a definite manner. In the liquid they are not, they are randomly oriented, that is why they can flow, right. But liquid crystal is a state or it is a distinct phase which lies between the liquid and the solid. So, that is why the name liquid crystal. What is so special about this? In liquid crystal, it has the properties of both liquid as well as crystal. What does that actually mean? It says that it can flow like liquid, but it has got order, it has got translational order similar to that of solid. The molecules have some degree of order, but they can also flow. So, that is why it is known as liquid crystal polymers. These liquid crystal polymers can show such a behavior either in the form of a solution or in the form of a melt. When they show such behavior in the form of a solution, they are called lyotropic. The word lyo means solution, that is why lyotropic. And the examples of lyotropic are aramids, aromatic heterocyclics, etc., which we have just looked at the structures. And on the other hand, the thermotropics means the ones which give such a liquid crystal behavior on heating or in the molten form, and the examples of this are aromatic polyesters. So, we are not going to look at aromatic polyesters in this, we are going to look at mainly the lyotropic structures in this particular module. So, what I am going to do is, by taking an example of aramid, I will be discussing how can the approach be suitably modified to get high strength, high modulus fibers using rigid rod structures, and the same approach can be applied to the other rigid materials as well. So, aramids, as I have already explained you, it is a paraphenylene terephthalamide, a polymer structure in which amide group is attached to the para position of benzene ring. In short, it is also known as PPTA, it is also known as Kevlar. Kevlar is the trade name of this fiber. Now, unlike the normal nylons, unlike the normal synthetic polyamides, nylon 6, nylon 6,6, we cannot melt spin aramid. You know why? Anybody can answer why? The reason is it degrades before it melts. The melting point is higher than the degradation point. Like cellulose, acrylic, they degrade before they melt, right? So, you cannot spin acrylic by melt spinning traditionally, commercially. Okay? So, these are also solution spun like we spin acrylic fiber. Not only this, dissolution is not an easy task, because these structures are very rigid and also they have interaction among the polymer chains, that means interchain interaction is there, the hydrogen bonding is there. So, therefore, you actually need to use very special kind of solvents to dissolve these rigid chains which exhibit very low solubility. You need to use solvents which are very strong, which can overcome these interpolymer interactions and then interact with the polymer chains. And the choice of solvent plays a very important role. Solvents with very high degree of interaction are required, something like HMPA, hexamethyl phosphoramide or NMP, N-methyl pyrrolidone. These are highly corrosive solvents, very difficult to handle. Or sulfuric acid, 100% sulfuric acid, not even 99.5, 100% sulfuric acid. So, these polymers exhibit liquid crystalline behavior when you dissolve in these solvents, and these liquid crystal solutions exhibit a very special kind of rheology which is very important. Let us see, let us understand what is the rheological behavior and why are these LCPs important. These are important because of their rheological properties. The reason is due to the special rheological properties, these polymers in the solution or in the melt form a very highly oriented structure, very highly oriented structures or domains, and such domains or highly oriented structures result in very high performance properties after spinning. So, that is how they contribute to the spinability or enhanced performance properties. Let us look at the liquid crystal behavior or the phase behavior of the solutions of these polymers. In this particular case, I am showing you PPTA, that is Kevlar or para-aramid solution in 100% sulfuric acid at a temperature of about 40 degrees. So, let us see, on the x axis I have concentration, while on the y axis I have viscosity, Brookfield viscosity, right. So, these structures which I am showing, the rigid structures actually show the rigid aromatic structure. So, when I increase the concentration, the viscosity increases, which is very normal for any polymer, for any material. You increase the concentration, the viscosity would increase. But what is abnormal is when I increase the concentration beyond a certain concentration, then these rigid structures, because of their rigidity, they tend to form domains, interactive domains, and these domains would flow in a preferential manner. They have a very special kind of flow behavior. So, this particular concentration, after this concentration, you notice that they form a very preferential oriented domains, and these domains are easy to flow. Easy to flow means the viscosity is low. Better the flow means lower the viscosity. Higher the viscosity means more difficult to flow. Okay? So, therefore, at this concentration what we notice is the viscosity suddenly drops. There is a sudden drop in viscosity beyond this concentration, which is attributed to the domain formation. And surprisingly, this concentration is also known as critical concentration. But please note, this critical concentration is different than the critical concentration in the case of PE gel fibers. This concentration, I mean the critical concentration, depends upon the temperature of the solution and the molecular weight of the polymer. If I have higher molecular weight, this concentration would reach at a lower concentration. This behavior would happen at a lower concentration. The critical concentration would come down. If I increase the temperature, again the critical concentration will come come down. Okay? And if I do the reverse, the critical concentration will increase. So, for making the fiber, I would like to use the concentration where the processability is good, that means the viscosity is low and the concentration is high. So, in this particular case, you just look at about 18-20% the viscosity is minimum, right. So, we choose a concentration of about 18 to 20% in this particular typical case for spinning, so that the processability is good and the solution is above the critical concentration. The polymer is dissolved in sulfuric acid at 80 degrees, and the point to note is the water should be absent. It is 100% sulfuric acid. Water cannot be tolerated. If water is there, it would lead to hydrolytic degradation at this high temperature. The PPTA concentration, as I showed you on the graph also, is about 18 to 20% is the most desirable, right. And using this solution, I can carry out the spinning in like I do it for the normal acrylic fiber. I use a coagulation bath. The coagulation bath can be water or it can be dilute sulfuric acid, because I have dissolved it in sulfuric acid. So, the coagulation bath should have a non-solvent. And another point to note is, importantly, the fibers must be washed thoroughly by dilute alkali, that is to neutralize the fibers, to remove the residual acid from the fiber. So much so that the bobbins are also washed to reduce the acid content to less than 0.01 weight%. If I look at the process of spinning, the dry jet spinning method, in which the spinneret is in the air, it is not immersed in the coagulation bath, right. The coagulation bath is below the spinneret, the fiber is spinning in the air gap, the dope is in 100% sulfuric acid at critical concentration, higher than critical concentration, and after the spinning the washing is being carried out using NaOH. If I see how does this structure result in very high performance properties. So, let us look at the zoomed view of what is happening near the spinneret. If I see here, the spinning solution has liquid crystal domains. That means the oriented structures are forming interactive domains which are all oriented along the flow direction. So, during the flow through the spinneret capillary, they all get further aligned along the fiber direction, and once they are out from the spinneret capillary, due to the elongational stretch that the fiber experiences, that the polymer solution experiences in the air gap, it further perfects the orientation of these domains, which is in contradictory to melt spinning, where the polymer will show die swell, right. And not only that, these polymers have very long relaxation time. Long relaxation time means they relax very slowly. So, therefore, before they relax, they are solidified, they are converted to the solid fiber in the highly oriented structure itself. This means that the highly oriented domain structure which was present in the polymer solution is also converted to the solid fiber because of the elongational stretch and the long relaxation time. So, what I would like to say is the highly crystalline and oriented fibers which are obtained in this case, they do not need any additional drawing. We do not need to carry out any additional drawing in the case of these fibers. However, a very short heat treatment in tension can result an increase in the crystalline orientation. So, very often these fibers, aspen fibers, are given a short heat treatment, and we notice that the modulus increases from 64 GPa to 150 GPa, almost 3 times, very high increase, and this is possible because there is a change in the fiber structure. The orientation angle changes from 12 to 15 degrees to 9 degrees or less. So, imagine a very short heat treatment for few seconds can result in such a high change in orientation. So, if I look at the properties of this fiber, that is Kevlar fiber, it has a density of about 1.45, strength 3.5 GPa, very high, elongation break is 3 to 4% like in the case of polyethylene, the tensile modulus is 125 GPa, very high. Compressive strength is not good, compressive strength is low, 0.35 to 0.45 GPa. That means, for application where you need to bend them, it leads to some kind of kink formation and the compressive properties are poor. If I look at the other rigid structure which we had looked at in the beginning, that is PBO, which has fused ring, 5-membered ring attached to the benzene ring. So, this structure is definitely more rigid compared to Kevlar. So, what are the properties that we expect? Let us have a look. In this case, the density is increased little bit because the structure is more rigid, can pack better. The strength is 5.9 instead of 3.5, very high. Elongation remains almost same. The modulus has become more than double. So, can you see how the structure is affecting the properties? So, it is because in this case the structure is more rigid, it can form more oriented domains. So, therefore, the mechanical properties which I get are also superior, although the compressive strength has come down, right. Now, look at another material, the third one, that is M5 or PIPD, which was the most rigid among the three, right. So, if I look at this material and if it is processed in the same manner to convert it to the fiber, then the properties which I expect are obviously even better than PBO, right. Let us compare. So, if I look at the properties are comparable, higher density, the tensile strength pretty high, 5 GPa, elongation break has even further gone down because the structure is more rigid. modulus is even higher than PBO, because the structure is more rigid, more oriented. And the interesting part is, in this structure the compressive properties are also better. What has led to this increase in compressive properties? Let us look at the structure of the three. In the case of Kevlar, there is hydrogen bonding between the NH and CO group, interchain hydrogen bonding, right. And in the case of PBO, there is no hydrogen bonding between the polymer chains, interchain hydrogen bonding is missing. So, therefore, PBO has a compressive strength which is lower than Kevlar. But the moment we go to PIPD, PIPD has a hydroxyl group which is at a very suitable appropriate position on the benzene ring. This hydroxyl group is able to form hydrogen bonding with the adjacent polymer chains on heat treatment, and it can lead to a 3-dimensional structure. That means, a structure in which there is a 3D hydrogen bonding. That means, in all the 3 dimensions, that means in the same plane as well as in the other plane as well. It is hydrogen bonded in all the 3 directions, whereas in the case of aramid or Kevlar, the hydrogen bonding occurs only in a particular sheet in one plane. So, therefore, it gives you enhanced properties with respect to compressive strength in the case of M5 or PIPD fiber. So, we have learnt the 2 approaches for making high performance fibers, and both the approaches have some limitations. The first approach which we discussed had a limitation of low melting point, right. The second approach does not have that limitation, but it has to be processed using very strong and corrosive solvents. Solvents like HMPA, solvents like NMP, solvents like 100% sulfuric acid. So, when you use these solvents, they also demand that the equipment which you use, the spinning machines which you use, the material of construction should be suitable, it should not get corroded with these solvents, right. So, the corrosive solvent is the limitation of the second approach. So, what is the way forward? What do you think one could do? So, now the future is, people are looking at nanomaterials or like carbon nanotubes or anisotropic inorganic nanostructures as reinforcing materials in the case of polymers. The normal polymers like nylon, HDP, etc. can be used, can be reinforced using these materials to enhance their mechanical properties. There is a lot of research which is going on in this direction. A lot of interesting papers have already been published in case of nylon, ZNO nanorods, nanowires based fibers, where a commodity grade material could be converted to a high performance material by simply using nanomaterials as reinforcing materials during the fiber formation. And mind you, in that case it was possible even by a normal melt spinning process. I would like to end here by completing the two approaches of high performance fibers, wherein we have learnt how to exactly opposite strategies can result in the same end result. Okay. So, in the next module or in the next part of the module, I will be talking about the stimuli responsive fibers. Thank you.